In this particular example, what we're trying to do is derive the product rule. We've been given the function k of x, which we are told is equal to the product of f of x and g of x. Well, if you wanted to start by finding the derivative of a particular function, you'd probably start using the definition. So you'll notice the first line in this derivation, as well as the first line already supplied in your study guide, reads as k prime of x equals the limit as h approaches 0 of k of x plus h minus k of x all divided by h. Well, the second line to this particular derivation is also supplied in your study guide and is seen here on the screen. If k of x is equal to f of x times g of x, then logically k of x plus h must be equal to f of x plus h times g of x plus h. So that's what you notice one of the big differences is in the second line of this derivation. We have k prime of x equals the limit as h approaches 0 of f of x plus h times g of x plus h. All of that represents the k of x plus h. Subtract f of x, g of x. The f of x, g of x represents the k of x from the previous line. And then that's all divided by h. In the third line of this derivation, what we've done is we have subtracted f of x plus h, g of x, and then added f of x plus h, g of x. So essentially, we have added 0 to the numerator. We have not changed the value of this expression, merely the way it looks. In the next line, what we've done is we've looked at the 4 terms that are found in the numerator of our previous expression, and we've grouped the first 2 together and the last 2 together. From the first 2, we can notice that f of x plus h is common to both of those terms. From the last 2, you'll notice that g of x can be common factored out. So that's what we've done. So on this fourth line of our derivation, we have the limit as h approaches 0 of f of x plus h, that was the term that could be common factored out of the first 2 terms, times g of x plus h minus g of x, and that's all over h, plus then from the second 2 terms, as we've previously mentioned, we could common factor out the g of x, so we have g of x times what remains, f of x plus h minus f of x, and then that's all divided by h. The next thing we've done is just split the limit apart. And then on the second last step, what we've done is evaluated the limit. The limit as h approaches 0 of f of x plus h would merely be f of x, because as h approaches 0, all you'd be left with is f of x. We haven't evaluated the limit for the other portion. We've just written the limit as h approaches 0 of g of x plus h minus g of x all divided by h. As we continue across, when we evaluate the limit h approaches 0 of g of x, since the expression g of x has no h in it, the limit as h approaches 0 of it would just be g of x. That's why it's outside of the limit sign now. And then what remains is the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Now if you look at that second line, you'll notice that the definition appears twice. We have the limit as h approaches 0 of g of x plus h minus g of x all divided by h. That is really g prime of x. Also, you'll notice we have the limit as h approaches 0 of f of x plus h minus f of x all divided by h. That is the definition of the derivative for f prime of x. So what we can conclude from that is that if we want to take the derivative of a function such as k of x, which is the product of f of x and g of x, its derivative, k prime of x, would equal f of x, g prime of x, plus g of x, f prime of x. And that's what's shown on the very last line of this derivation.